So we will start with a brief introduction of the workshop. Then we will follow the schedule of the workshop. So let's get started. So all we care about robot manipulation because we hope one day robot can help people to do tasks in the human environments. So in the future, we imagine robots will assist our senior citizens, assist the disabled people, and serve people in various places. We hope to have robots that can cook a meal, clean a kitchen table, or load the dishwasher for us at homes. The core components in all these applications is related to robot manipulation. So robots need to manipulate objects in order to perform tasks, and robots need to use tools to perform tasks. But robot manipulation is still a very challenging and unsolved problem. Representations for manipulation is very important. In the following slides, I will give a brief introduction of the current representations people use for robot grasping. Then we will discuss the pros and cons of these representations. The most straightforward representation for grasping, we can use images. Here's an example. The DexNet, which is proposed for top-down grasping, takes an input depth image and outputs the top-down grasp of objects in the depth image. Given the planned grasp, we can do some motion planning and control the robots to follow the motion plan and eventually reach the top-down grasp. So you can see in this example, the representation is an image. The network takes the whole image as input and output the grasps. We can also use 3D object models to represent objects. In the traditional pipeline of perception, planning, and control, suppose we have the 3D models of objects. In perception, we can tackle the 60 object pose estimation problem. So this technique can detect objects, estimate their 3D location and 3D orientation. So given the 3D location and orientation of these objects, and we assume we have the 3D models, in the planning phase, we can set up a planning scene for grasp planning and motion planning. So in this example, this algorithm will plan a trajectory of the robot arm to reach one of the objects. So given the motion plan, we can control the robots to follow the motion plan and eventually grasps the picture base in this example. So you can see in this traditional pipeline, the representation is the 3D object model for objects. Or we can use point clouds to represent objects. Again, in this pipeline of perception, planning, and control, in perception, we can tackle the object instance segmentation problem. Suppose given an input image, we segment objects, and we assume we have depth image from the depth sensor. We can get the point clouds of each segmented objects. Then in planning, there are some algorithms. They can plan grasps given the point clouds of objects, such as grasp net or contact grasp net. So in this figure, you can see this green fox. They indicate the planned grasp, which is collision-free, and the red fox, they are grasps that are in collision with other objects. So given these planned grasps, we can plan a motion trajectory to reach one of the grasps, and then in control, can control robots to follow the trajectory and grasp the objects. So in this case, the representation is a point clouds of objects. So here's a short demo to illustrate. Suppose we combine segmentation and the point cloud-based grasp planning. We can enable fetch robots to pick up objects on a tabletop. So on the left, you can see the RV view. You can see the segmentation results and the movie motion planning scene. On the right, you can see the real robots executing the grasps. The representation for this grasping is based on point clouds of objects. Okay. So I have briefly discussed these three representations for robot grasping: images, 3D object models, and point clouds. They have pros and cons. For example, if you use images, that's the easiest sensing information can get. But the drawback is that it's hard to generalize. We might need to have a lot of training images for specific task or for specific domain. If we use 3D object models, it's not scalable. We cannot get thousands of 3D models for many objects. Also, for some objects, such as transparent objects or metal objects, it's hard to get their 3D models. If we use point cloud, we're limited by the depth sensing capability. The current depth sensors, they have limitations in sense transparent or reflective objects. So then this motivates us to think about, can we have better representations for robot manipulation? If we look at the computer vision or computer graphics community, researchers have introduced new representations for 3D objects. For example, the deep SDF network, it encodes the standard distance function of a 3D shape into a neural network. Given X, Y, Z query points, the network will output the standard distance function value for that specific points. And in this case, the network implicitly encodes a 3D shape. So similarly, the NeuRL model, it encodes both geometry and appearance information into a network. Given a query point's X, Y, Z position, NeuRL will output the color information as well as the density at that point. So then it encodes both geometry and appearance into a single network. So then we start to think about, can we leverage these new representations or implicit representations to help or to improve robot manipulation? On the other hand, vision language models receive a lot of attention these days. For example, the CLIP model proposed by OpenAI, they encode both images and the languages into a shared common embedding space. In this case, we can connect the two modalities. Given images, we can retrieve the closed text, or given text, we can retrieve the closed image. So then by leveraging these vision language models, we can connect robot manipulation with languages. So then why we care about these new representations or implicit representations? Because we think we can learn new representations for arbitrary objects. For example, suppose we use 3D models, they are limited by rigid objects. But we can learn new representations for arbitrary objects using the raw sensor image. For example, here are some objects, we can learn representation for them. These are rigid objects, deformable objects, articulated objects, or even granular objects. By using vision language models, we can also connect robot manipulation with languages. So that's why here we are. We're trying to explore how can we learn new representations to help robot manipulation. With that, I'll hand over to Kasik, who will introduce some details and logistics of the workshop. Thank you.
Thanks, you. So I think we wanted to, when we were organizing this workshop, we wanted to bring experts from the robotics community to come together and talk about what we mean by neural representation learning, especially in the context of robotics manipulation, because a lot of the work has been done in computer vision and graphics. We hope to have a nice arena where you can have insightful discussions on what other people think about neural representations learning and so forth. So here are some questions that you might want to linger about throughout the day. So when you talk to the speakers or when you talk to the presenters, so think about these questions so you have a fundamental grounding on what we mean by neural representation learning. So think about what neural representations are useful for robotic manipulation. What should a neural representation capture? Is it about geometry? Is it visual appearance? Is it dynamics? Is it all of them together, or are we missing something? How to learn and use these neural representations for robotic manipulation. So talk about data sets, simulation environments, sim to real. How can we leverage advances that are happening in computer vision and graphics and so forth. And last but not least, do talk about how to benchmark the progress in neural representation learning. So this is a great way to think about making progress in this particular field as a community. So think about these questions throughout the day when you are interacting with people. I think that will be super useful. So Speaking of experts in the field, we have 6 amazing speakers. So we have Shiran from Stanford, David from CMU, Georgia from TU Darmstadt, Pete Florence from Google DeepMind, Chris Paxton from Meta AI, and Chad Jenkins from University of Michigan. So we tried our best to bring in people from industry and academia, so we can talk about this particular topic. So alongside, we have 11 poster presentations. So they have a spotlight. So we have 2 spotlights, one in the morning and one in the afternoon. So the posters are going to be outside this hallway. So for you to engage in discussion. So the posters will be out for the entire day. So you can look at the posters as well. Okay, coming back to organizers. So I'm Karthik Singh. I'm an assistant professor from University of Minnesota. I'm super excited to be co-hosting this workshop with Professor Chung-Yun Choi from University of Minnesota, Professor Yu Xiang from UT Dallas, along with students. So Jishnu, Ninad, Sai, they're from UT Dallas, and Ali Reza, who is from University of Minnesota. So here is the schedule. So after we are done with introducing, we'll have our first speaker, followed by spotlight presentations. And we'll break for posters, and then we'll come back for the invited talks. We'll break for lunch, come back for invited talk, followed by spotlight presentations. And towards the end, we'll end with a couple of invited talks. So we initially planned for a panel discussion, but we're not going to have that. We'll have a concluding session around 5 o'clock to kind of conclude the workshop. So with that, I also want to highlight that the posters initially were scheduled to be in Muse 1. But this is going to be in the hallway now. So just so you know, it's not going to be in Muse 1, it's going to be in the hallway. With that, I'll have Chung-Yun